Now we'll discuss the problems in the fourth assignment. The first problem, it's about nodal analysis, and essentially you have to determine in the nodal analysis equations. Okay, and this circuit is the easiest case for nodal analysis. It has only resistors and independent current sources. Okay, and the nodes are already marked. There are three nodes, 1, 2 and 3. So all you have to do is pretty much stick to the standard algorithm for writing down the equations. This is the G matrix. The diagonal entries are the total conductance at each node. So first you have to convert these things to conductances. That's the only thing you have to do. 5 kilo ohms is 0.2 millisiemens and 2.5 kilo ohms is 0.4 millisiemens. Okay. So at node 1 we have 0.2 plus 0.4, which is 0.6. At node 2 we have 0.4 plus 0.4 plus 0.2, which is 1. And at node 3 we have 0.4 plus 0.4, which is 0.8. Okay. And then between node 1 and node 2 we have 0.4 millisiemens. So it appears as minus 0.4 there and there. It will be symmetrical. Between node 2 and node 3 we have again a 0.4 millisiemens conductance. So that appears as minus 0.4 minus 0.4. And between node 1 and 3 we have nothing. So this will be 0 and 0. The right hand side of course is the independent sources which are going in. So into node 1 we have plus 2 minus 1. So this is 1 milliamp. And node 2 we have plus 3 plus 4 minus 2. So 3 plus 4 minus 2 is 5. And finally node 3 we have minus 10 minus 4. So minus 14. Okay. So that's the setup. And in the first question you are asked only for the G matrix. So the answer is this one, and you have to write only these entries. Okay. And you are asked to find the voltage at node 3. That's very easy. All you have to do is to invert this and multiply it with the source vector, and the answer turns out to be minus 18.75 volts. Okay. The next problem, a circuit now has resistors, independent current sources, and also a voltage controlled current source. Okay. So again the nodes are marked and so on. First of all, let me write down the contribution of only the conductances. Okay, this first row corresponds to node 1, node 2 and node 3, and this is V1, V2 and V3. Okay, so first I'll write down the contribution only due to conductances, and again 5 kilo ohms is 0.2 millisiemens and 2.5 kilo ohms is 0.4 millisiemens. So here we have a total of 0.6, and here we have a total of 0.2 plus 0.4 plus 0.4, again 1, and here 0.4 plus 0.4, 0.8. And between nodes, between 1 and 2 we have 0.4 millisiemens, and between 2 and 3 we have 0.4 millisiemens. And between 1 and 3 we have nothing, so that is 0. Now we also have this current source here. If you look at the current flowing out of node 3, okay, so that will be 0.4 millisiemens times Vx, which is V1 minus V3. Okay, so this will add to the equation for node 3. Okay, so what will we have? We will have the coefficient of V1. By the way, this will be the coefficient of V1, this will be the coefficient of V2, this column is for V3. So to node 1 we have plus 0.4, and node 3 we have minus 0.4. Okay, so if you sum them together you will have 0.4 this will remain as it is, and this will be also 0.4. So the three rows are this, this and that, and that's what you have to enter as the answer. Okay, and you need this for the next part. You need the source vector, which is basically the total source current to each node. So to the first one we have minus 0.9 milliamps. Okay, I'm not writing the units here, this is in milliamps. And here we have minus 3.6 coming in, so this will be minus 3.6. And here we have 14.4 going out, so again we have minus 14.4. Okay. And now here you have to find the power dissipated in Rx. How do you do that? Rx is this one, okay, and the voltage across Rx is V2. The power dissipated in Rx would be V2 square divided by Rx, or V2 square divided by 5 kilo ohms. Okay. So that's what it's going to be. So by inverting the G matrix and multiplying it with the current vector, you will get all the voltages. From that you find V2 and you calculate V2 square by 5 kilo ohms, and you will find that it is 180 milliwatts. Okay, so that's the answer. The next one, again to set up nodal analysis, this time we have a current controlled current source. Okay, now the current is flowing through some resistor, so that part is easy. Again, I'll set up the G matrix. The first row is for node 1, second row is for node 2, third row is for node 3. First column is the coefficient of V1, second column is the coefficient of V2, third column will be coefficient of V3. Okay. Now again, first I will consider only the conductances in the circuit. We have 2 kilo ohms, which is a 0.5 millisiemens conductance, and 1 kilo ohm, which is a 1 millisiemen conductance. Okay, so the total here is 1.5, and the total here is 1 plus 1 plus 0.5, so that is 2.5, and the total for node 3 is 1 plus 1, which is 2. And between nodes we have 1 millisiemens between node 1 and node 2, so we have minus 1 and minus 1. We have 1 millisiemen between node 2 and node 3, so minus 1 and minus 1, and nothing between node 1 and node 3, so that is 0. Now these are only due to conductances, but we also have this control source, and this is pushing a current into node 3, or if you look at the current going out of node 3, what is that? That is minus 2 Ix, and Ix itself is how much? That is the voltage difference between these 2 points, node 1 and node 2, divided by 1 kilo ohm. Okay. And this turns out to be minus 2 millisiemens times V1 plus 2 millisiemens times V2. Okay, so to the coefficient of V1, this of course is for node 3, so it belongs to the third row, and the coefficient of V1 we have an extra minus 2, coefficient of V2 we have an extra plus 2. Okay, and you sum the corresponding ones, you get minus 2 here, you get plus 1 here, and this remains as it is 2. Okay, so this is the conductance matrix that you have to enter as the answer. The right hand side, again quite simple. The total current coming into node 1 is plus 2 minus 1, so that's 1. Total current coming into node 2 is plus 1 minus 2, so that is minus 1, and into node 3 is plus 3. Okay, all of these are in milliamperes. And you have to find the voltage at node 3. Again, all you have to do is solve for it, G inverse times I, and the voltage at node 3 turns out to be 2.35 volts. Okay. again yet another nodal analysis setup, but this time we have an independent voltage source. So we have to treat 2 and 3 as super node and write the voltage source equation separately. Okay. So there will still be 3 rows, and node 1, node 2 and 3, the super node and the voltage source. These are the 3 equations we will write. The first column will be coefficient of V1, second one coefficient of V2, third one coefficient of V3 as usual. Okay. Node 1, the total conductance is 0.5 millisiemens plus 1 millisiemen, so that is 1.5, and here this is considered as a super node, so we need to consider the total conductance connected to node 2 and node 3. Okay. So here the second row corresponds to the super node. Okay. So the total conductance connected to node 2 and the total conductance connected to node 3 will both appear in this row. Okay. Node 2 we have 1 millisiemens plus 0.5, so that's 1.5, and node 3 we have just 1. Okay, both of these will appear in this row, and between node 1 and node 2 we have 1 millisiemen, so that will appear as minus 1 there. Okay. That is 0. And finally the voltage source equation, you can see that it is V3 minus V2 will be 11 volts. Okay. So that's the equation. So we have minus V2 plus V3, and here the current vector, I call it current source vector, but it has both currents and voltage sources. So the third entry will be 11 volts, it will be in volts. Okay. And the first one will be the total current into the first node, 12 minus 1, which is 11 milliamperes, and the second one, it is 12 going away and 8 coming in and 18 going away. Okay, because this is the super node, the total current going into the super node is plus 8 minus 18 minus 12. Okay, so which comes out to be minus 22 milliamperes. And even the G matrix, these are all in millisiemens. Okay, whereas the last row, it has dimensionless entries. Anyway, in this case, you have to enter the G matrix entries, which means this is the matrix that you have to enter. Okay. And you have to find the voltage at node 2. So you have to find G inverse times I. Because you have conductances and dimensionless numbers, you have to take the conductance also while calculating the inverses. Okay. Or in this, if you have everything in Siemens and here you have amperes and volts, things will be consistent. Similarly, if you have everything in millisiemens here and milliamps and volts, that will also be consistent, and so on. Okay. And this voltage at node 2, this turns out to be minus 14 volts. Okay. So that's the answer. And here in this case, we have a voltage controlled voltage source. This is not an independent voltage source, but a voltage controlled voltage source. But again, the same procedure. The first row will correspond to node 1, the second one to the super node of node 2 and 3, and the third one will be the voltage source equation. That is, in this case, it's the voltage controlled voltage source. Okay. And first column, second column and third column are coefficients of V1, V2, V3 respectively. And in fact, you would have realized that this circuit is the same as the previous one, which was the same as the one before it. So you should be able to use the results you already have. The total conductance from first node is 1.5 millisiemens. From the second node, it is again 1.5, and the third node, it is 1. Both of them appear in the second row, which corresponds to the super node of nodes 2 and 3. Between node 1 and node 2, we have 1 millisiemens, so we will have that, and this will be 0. The voltage controlled voltage source equation, it is between 2 and 3, so V2 minus V3 will be basically equal to Vx, which is V1 minus V2. So you can write this as V1 minus 2V2 plus V3 is 0. So coefficient of V1 is 1, this is minus 2, this is 1, and this whole thing will be equal to 0. These are dimensions of conductance, they have units of millisiemens. And in the current source vector, the first one, it has 12 plus 1, 13 milliamperes. Second one, it has 5.5, that is going in, minus 2.6, minus 12. Okay, and this corresponds to minus 9.1 milliamperes. Okay. The last question is to determine the voltage at node 1. So again, you invert the G matrix and multiply the source vector with it, and you will find that the voltage at node 1 is 11.2 volts. Okay. So that brings us to the end of fourth assignment.